So just a little bit the title, and then first I would like to show you a small life hack about integration, which I learned a few days ago. So first, a small trick for integration by part. Integration by parts. If you know it, just tell me, but probably you don't know it. So all of you, I hope, know integration by part, because it's a standard technique. So if you'd like to find the integral of u prime v dx, then this integral could be replaced by what? Just a small recall. What is integration by parts?
Well, it's uv minus integral uv prime.
Yeah, exactly right. But my trick is not about this the integration by parts itself, but if I apply it twice, I see that I just point out that u has one derivative less, and v has one derivative more. So u goes to u prime goes to u, and so probably u prime goes to u, and v goes to v prime, and so on. And basically, if I will do the same step, I can do the same step second time. If I do it twice, or 3 times in a row, or 4 times in a row, basically what will happen, v will be v prime prime, and u will be like integral of u dx, and so on. And basically I can make a table, and with the table I can do it faster. So the trick is to make a table. Probably you know it, but it was completely new to me. Obviously I know integration by part, but this trick with table was completely new to me. So let's, for example, find an integral of x cube, exponent of I don't know, minus 1/2x dx, for example, like that. And so what I do, I create, to make it to calculate it faster, what I do, I build a table, I take x cube, and I calculate the derivative. It will be 3x squared, then 6x, then 6, then 0. And if I take exponent of minus 1/2 of x, I take integral or antiderivative integral. So it will be minus 2 times exponent minus 1/2x. And once more, it will be minus 2 squared exponent minus 2x, minus 2 cube exponent minus 1/2 of x, and minus 2 to the power 4 exponent minus 1/2x. Okay, the table is clear. Yeah, what I'm doing, I'm just doing the same process but faster in table. And basically, let's see what is multiplied by y. But what? U times v. I should always, on each step, I should add uv, but the sign will alternate because I have minus on each step that is added. So basically, I take uv. This is u, this is v. So basically, I take the diagonal product like this with plus. Then I take the next diagonal product with minus. Why with minus? Because it will be minus integral on the next step. The next product of uv is with plus. Once again, the next product of uv is minus. and integral of 0 times something will be 0. So I need to take that one with plus, but not 0. So I write immediately the answer. So very fast. I just write the answer. Yeah, it will be x cubed times so it will be I write x cubed times minus 2 exponent minus 1 over 2x. This one with plus. Next one with minus 3x squared minus 2 squared exponent minus 1 over 2x. And the next term with plus 6x minus 2 cube exponent of minus 1 over 2x. And then the last one was minus 6 times minus 2 power 4 exponent minus 1 over 2x, and add plus constant. Yoo-hoo. Yeah, that's okay. Or you are familiar with this trick because it was completely new to me.
I think it's okay. Yeah.
Yeah, that's clear.
But that's new. Yes, that's new.
Yeah, okay for me.
So basically, I do the same thing, but two in a table, and I just write the answer. And I have applied integration by parts 1, 2, 3, 4 times in a row, or to be honest, 5 times in a row too. So I have done 4 times, four times in a row, I have done integration by parts, which is great. 4 times in a row instead of just 2. That's very fast. Just to check whether you understand the technique, just try to find an integral of, let's say, x squared plus 5x times cosine of x dx. So just try it by yourself. What is the answer? So just 1 minute. Just 1 minute. That's very fast with the table. Just that's. And it's less prone to errors because you have derivatives and antiderivatives in table. And I think you are not opening brackets, closing brackets. So it's faster. You make less errors. So it was completely new to me, this way to write integration by parts in a table. Okay, is it fine?
Well, I think I'm ready.
Yeah. So let's to check easier. Let's start with the table. So we have a table x squared plus 5x. Below we have what?
2x plus 5.
Yeah, we have 2x plus 5, and then we have 2, and then we have 0. On the in the right column of the table, we have what?
Integrals we start with cosine, then sine minus cosine.
Integral of cosine is
sine,
yeah.
then minus cosine, and minus sine.
Minus sine. And that we do not need anymore. Okay, and then we write the answer. And then just the answer. We just look at the diagonal products. We start with plus, we alternate the sign, and the last one we do not need. Okay, so the answer should be x squared plus 5x times sine of x. minus 2x plus 5 times minus cosine of x plus 2 times minus sine of x. And do not forget integrating constant. Yeah, that's fun.
Thank you, it's funny.
Okay, let's move on. So maybe the last point, even if it doesn't go to 0, sometimes obviously it will not go to 0, but in that case you may use equation. Yeah, for example, the last case probably is something like if you integrate cosine of x times exponent of minus 5x dx. So it's better again to start with the table. I go with cosine of x, exponent minus 5x. So here I will calculate derivative, or in the right column, I will calculate integral. So it will be derivative of cosine, it's minus sine. And I have minus 1/5 exponent minus 5x. Then I see that it is minus cosine of x. That is minus 1/5 squared minus exponent minus 5x. I see that the process will never reach 0. So obviously, when I take the derivative of cosine, it will never reach 0. But if I'm on the line, so this is just integral of product. So that is the integral of product. And basically, I could write the answer. So it is, so I start with diagonal. It's cosine of x minus 1/5 exponent minus 5x minus sine of x times minus 1/5 squared exponent minus 5x. And then the next one should be with plus, but it's with plus integral. And I write, that is the row. I write, if I will not obtain 0 in the first column, I just write 0. Integral of minus cosine of x minus 1/5 squared exponent minus 5x dx. And basically, that's all. I will just move on the last term on the left-hand side. I will obtain that 1 plus 1/25 times my integral is, oh, okay, so that's basically finished. I will write the answer completely minus plus sine of x 1/25 exponent minus 5x plus c. And so basically, I will just divide by 1 plus 1/25, and I will obtain my integral I. And this is I'm searching. Okay, any questions about this trick?
Well, it's a really cool method, but how we should explain it on the exam, for example?
I think you don't need to explain it.
Like we can just write it?
Yeah.
Okay, thank you.
Okay, so let's move on to the linear programming. Linear programming. Okay, let's solve some stuff with parameters in linear programming. So let's consider the following problem. We will minimize x1 plus x2 plus 2x3 plus 4x4. Will minimize that subject to all variables will be non-negative.
Wait,
And
isn't
then,
it 4x4?
yeah, you're right. And inequalities are lambda times x1 plus x2 minus x3 plus x4 is greater or equal than -1, and x1 plus 3 over 2 x2 plus x3 plus x4 is not less than 5. And the exercise, the goal of the exercise to find the minimum, the minimal value. So we need to find, so let's run this q x1, x4, and the exercise asks to find q star that depends on lambda. So our goal is to find not the optimal point, but the minimal value. Okay, the goal is clear.
Yes.
Yeah, so to find the minimal value as a function of lambda.
Yeah, the goal is to find the optimal value as a function of parameter. So for every possible value of the parameter lambda, we should find the best possible value. Okay, the goal is clear.
Yes.
Yep.
Okay, how we will solve it? What are your ideas?
Can we switch to two variable case?
Yeah, exactly. That will be our strategy. Obviously, we can go blindly without appealing to a graphical solution. Yeah, obviously we can do like that. Just let's write Lagrangian function and blindly without graph. That's okay. That's a possible way, but it will be very hard because you will have a system of a lot of inequalities. We need to introduce two lambdas, let's say mu1 and mu2. And to solve a system of equations and inequalities with a parameter, that you need to consider a lot of cases blindly without any intuition, and that's possible, but that's a crazy idea. So you are completely right that it's better to switch to two variable dual case, because there we will have intuition. We can look at the plot, and that's much better to consider cases on the plot. That's even that is a little bit, we need to be attentive to cases, but that's much easier. Yeah, I strongly agree with you that it's we can, yes, that my point, we can solve this problem just blindly, just apply the first order condition and go on. That's a possible strategy, but it's a, you're right, that's a great idea. Switch to dual. That's a great idea. Okay, let's switch to dual. So first step will be, you are completely right. How we switch to dual? Who can state the dual problem?
Well,
Well, it's minus.
Yeah. Anyone?
Okay, minus y1.
Okay, yeah, minus y1. We maximize, minimize it.
Maximize.
Yeah, we maximize it. Minus y1
Plus 5 y2.
plus 5 y2. Okay.
Yeah, subject to
Mm-hmm.
lambda y1
Lambda y1.
plus y2
Uh-huh.
less than 1,
Uh-huh.
then y1 plus 1.5 y2 less than something, yeah.
60.
And then analogously,
Yeah, any questions how to switch to dual problem? So the first step is done.
Now we should probably draw a graph. It will be more convenient
Yeah.
like this.
Yeah, you're right. Yeah, let's draw a plot. So I advise you to first to start with constant lines that are not affected by parameters. So I will start with drawing the last three constraints. And the first one, it will depend on the value of the parameter, but we will draw it. Okay, let's draw it. So we always work in a region where y1 is positive, y2 is positive. So let's start with the second one. Y1 plus, it will be 6. It will be, I think, 4. Yeah, that is the second one. Then we go to the third one. So it is the first one. I have ignored that for the moment. Number 2, number 3, number 4. Number 3, it will be y2 is 2. And it will go from like that. It is number 3. Number 4, what will I get? I think it is like this. Or it is number 4. And then we need to work with the first one. What it will be? What will lambda change? What will lambda do?
slope.
Sorry?
Slope.
Yeah, exactly. When I will change lambda, it will rotate my curve. So I will find the point that is always on the curve. And then I understand that lambda will rotate my line, basically, which point is always on the curve. So now I consider lambda times y1 plus y2 is less than 1. So which point is always on this line? So if L is given by, let's consider equation, if which point A is always on curve?
0, 1.
Yeah. I agree. So the point A01 is always on the curve. So 0, 1 is somewhere here, that is A. And then I should, yeah, it's better to write also level curves. So it's better to write also level curves of the our goal function. Where it is. So I need to maximize, yeah, maximize minus y1 plus 5y2. Or if I make a level curve for this goal function, it will be y2 is c over 5 plus y1 over 5. And so it is a very small positive slope, very, very small positive slope. And basically, that is very small positive slope. And I will move it up and down by correcting C. Any questions up to now?
Thank you. No question.
Okay, so let's rotate the curve number 1, L1. Yeah, let's rotate it. What are the important points? The important point will be when my curve passes through some interesting points. So that one will be interesting. That one will be interesting. There will be interesting case when the slope of my line number 1 coincides with the slope of the goal function. So when it is like very slightly, very slight, very slight, like this, like slope equal to 1 over 5. That will be interesting case. Probably that's probably I think that's probably all. That's probably everything I need. Okay, so let's consider all possible lambdas. So lambdas are in range from -infinity to +infinity. And now I calculate the lambda for each interesting case. So that will be, let's name them. So let's call this point B. This will be B, this will be point C, and this will be point D. So I will consider I have too much to do, and that's end of page. Oof, that's a little bit, I don't like it. So I will try to copy. So just a moment, I will copy my, or even Okay, I have copied everything I need. Then we may go on. So I will consider cases B, C, and D one by one, because I don't know any better strategy. So I will just consider cases one by one. So I will consider case B. Case B happens when I have intersection of all the lines. So I have intersection of line 1, lambda y1 plus y2 equals to 1. I have intersection of line 3 and line 4. Line 3 is how was it awful with such a small. I've forgotten the line number 3. Let me recover it. It will be minus y1 plus y2 equals to 2. That is line number 1. That is line number 3. And line number 4 is line number 4 is y1 plus y2 is 4. Like that? Yeah. Case B. Anyone is with me?
Yes.
Okay. So I just calculate the coordinates of y1 and y2. I sum equation 3 and 4, and I obtain 2y2 equals to 6. y2 is 3. And then y1 is 1. And basically lambda plus 3 is equal to 1. Then lambda is minus 2. Okay, so I know case B, lambda is minus 2. Let it be here, minus 2. Lambda is minus 2. That's case B. Okay, let's move on. Let's consider case D. Case D. The slope of my rotating line is equal to 1 over 5. And basically, y2 is 1 minus lambda by 1. From the other hand, the slope is minus lambda. And so lambda is minus 1 over 5. So case D is here, lambda minus 1 over 5. And I need case C. Case C, my curve lambda y1 plus y2 equals to 1 should pass through the point C. And C has coordinates 4 and 0. Yeah, 4 and 0. And that means that lambda is 1 over 4. Okay. Lambda is 1 over 4, case C. Have you the same results, guys?
Yeah.
Okay, if you have the same results, then let's consider, well, let's look at our scheme for lambda, and let's rotate the red line. Okay, now we are rotating the red line. Let's start with minus infinity. So if the lambda is minus infinity, then I have a very, very positive curve. Yeah, that is before the case B. I have a line like that. Oh, that is. In that case, on this segment, if I consider this part of lambdas, the optimal point will be at point B. Yeah, if I my possible region, or maybe it's better to draw each case by part. Yeah. So in a case, so let's draw it for each case separately. Yeah. Because that's maybe it would be better. So I have a plot like that. This is B, D, C, and my red line is before B. So the possible region is like this. Lambda, so that is lambda belongs to from -infinity up to -2. And in that case, the optimal will be there. B will be the point of optimum. Okay. And I can easily calculate the optimal value. Optimal value will be at B. I have optimal value. My goal function is -y1 plus y2. Coordinates of the point B are here. So I need to calculate -y1 plus 5y2. -y1 plus 5y2. And it's equal to -1 plus 5/3. And as if I'm not mistaken, it's just 14. Okay.
Yes.
So now let's move on. I will draw faster my subcase. Oop, oop. This is B, this is D, this is C. If lambda changes from -2 up to -1/5, it was -1/5, yeah?
Yes.
So the line goes like that. My first line, line 1, goes like that. And the optimum of the region in which I'm allowed to be in that quadrilateral. And the optimal point will be this moving point. Woo! And will be moving point, let's call it X. Woohoo! That's very hard. We have an optimal, so this is a goal function, this is y1, this is y2, and x is the optimal point. So I need to calculate the coordinates of x. X star will be the intersection of line 1. Intersection, I have forgotten the number of the line which goes from B to C. It was
4.
which one?
4.
4? That is 4, yeah?
No.
Okay, so I calculate lambda 1 y1 plus y2 equals to 1. This is line 1. And intersection with line 4, that is y1 plus y2 is equal to 4. The intersection is y1 multiplied by 1 minus lambda is 3. So y1 is 3 over 1 minus lambda. And y2 is 4 minus 3 over 1 minus lambda. So that's coordinates of the point x star. And the optimal value, if you remember, it's minus y1 star plus 5 y2 star. And it will be, maybe it's better to simplify, it's 4 minus 4 lambda minus 3 over 1 minus lambda. It's 1 minus 4 lambda over 1 minus lambda. And so basically I get the optimal value in that case, minus 3 1 over lambda plus 5 minus 20 lambda over 1 minus lambda, and it will be 2 minus 20 lambdas over 1 minus lambda. Okay?
Okay.
And the last, I think, what we need to do this is B, this is D, this is C, this is my A. If I have a line that goes with very, very, very small, even smaller than 1 over 5. So the region I'm allowed to be is that red quadrilateral. Is lambda belongs from minus 1 over 5 up to plus infinity. This is y1, this is y2. Where will be the optimum? So where is the optimum?
0, 1.
Where?
0, 1.
Yeah, exactly, in the point A. Yeah, A will be optimal point. Optimal point is A star. Yeah. So y1 optimal will be 0, y2 optimal will be 1, and optimal value will be minus y1 plus 5y2 will be minus 0 plus 5 will be 5. And then I just collect everything. I need to consider border cases, but because so the point moves continuously, yeah, and so as the optimal set changes continuously, I understand that on the border case, so in the point D, for example, when my line will go through the point D exactly, because of continuity, the maximum will be also 5. Because at the point D, the optimal value should be approximately equal to the optimal value at the point D plus minus epsilon, if I move it by epsilon to the left, to the right, in any side. Oh, and bingo! I just will write the answer. Finally, I have the answer. Q optimal value that depends on lambda has basically 3 cases. I can attach special points to any case because of continuity. So it doesn't matter where you will attach these points where we have a switch from one case to other case. Basically, we need to have lambdas that is below -2 lambda from -2 up to -1/5, and lambda from -1/5 up to plus infinity. So I have three cases that you should attach somewhere these special cases, but it doesn't matter whether you will attach them. So for example, you may glue these -2 to the first case, or glue -1/5 to the second case. That doesn't matter. You should glue them somewhere, but it doesn't matter where you will glue them. Okay, and the answer is, as far as I remember, it was 2 minus 20 lambda over 1 minus lambda. Here it was 5. And honestly, I don't remember, it was 15 or 14 or something like that in the first case. Who remembers?
It was 14.
It's 14. We just check. We have a check because of continuity. When you move a point, so the value of a linear function changes continuously. Then let's check if lambda is -2. So let's check continuity. Let's check when lambda is -2, then 2 minus 20 times -2 over 1 minus -2 is 62 divided by, oops, something is wrong. 42 divided by 3, and that's okay. That's 14. Yeah, that's great. And let's check continuity. And if lambda is -1/5, then 2 minus 20 minus 1/5 divided 1 minus 1/5. It will be 2 plus 4 divided by 6/5, and it will be 6 times 5 divided by 6. It will be 5. Yeah, that's great. My function is continuous. I can even draw it. So this is lambda. This is the optimal value that depends on lambda, and it is -2 minus 1/5. It is 14, 5, and then it goes to, so it is 14, it is 5. It goes like that. Any questions?
Yes, I have a question. So how do we know that y1 and y2 should be bigger than 0?
Where do you mean?
So it was like in the first part. So when we switch to the new variables.
Yeah.
Yeah. So we assume that y1 and y2 are bigger than 0.
Yeah. I forgot to write it. Yeah. Y1 is greater than 0. Y2 is greater than 0. Yeah, I have forgotten to write that. But you are right. They should be greater than 0. Why do we know it? Basically, during the lecture, we have proven that these two problems have the same second order, the same first order conditions. Why? Because x1, x2, x3, and x4 are Lagrange multipliers for inequalities with y. And y1, y2 are Lagrange multipliers for inequalities with X. And basically, when you write first order conditions, Lagrange multipliers should be non-negative. So when you will write first order conditions for the first problem, you will write y1 and y2 should be non-negative because they are Lagrange multipliers for the problem with x, 1, x2, x3, x4. And when you will write first order condition for the second problem, the problem with y1 and y2, you will write that Lagrange multipliers for the second dual problem are non-negative, but Lagrange multipliers will be x1, x2, x4. So in both problems, both original variables and Lagrange multipliers should be non-negative. And during the lecture, we have shown the case accurately that first order conditions exactly match. So there is a perfect match with first order conditions of these two problems.
Yeah, thank you. And I forgot about the sign of Lagrange multipliers. Does it depend on whether we maximize or minimize the function?
So basically, yes. But in our case, we have switched the sign twice. So that's why it's important that we have problems in standard form. So basically, you're right that when we switch minimization to maximization, we should switch the sign of lambdas. But we have switched not only maximization to minimization, but we also switched the direction of inequalities. So in that problem, it was minimization with greater than 0. So if we move -1 to the left-hand side, our inequality they look like greater than 0. And the problem is minimize something. If we consider the dual problem, if we move everything to the left-hand side, the inequalities are reversed. They have less or equal than 0. So we have changed sign twice. We have changed minimization to maximization, one change, and every equality of type greater than 0, oops, we have switched to less than 0. And so we switched the sign twice, and that's why lambdas in both problems should be non-negative. Okay?
Yeah, okay. And so if there was a maximization problem initially, the lambdas would be negative.
So you may do like that, but I prefer to always standardize and do not care about it at all. So if I have a question on the exam like minimize x1 plus 6x2 plus so on, and the first one is x1 plus 2x2 minus x3 is less than 5. So I will, and the second inequality is 2x1 plus 3x2 plus 2x3 is greater than 6. I see that I have minimization problem, but oops, I have a problem there. So I will just multiply my inequality by -1. I will standardize the problem, and it's better to always work with non-negative Lagrange multipliers. You can state separately that first one is negative, second one is positive. You can do that, but it will be a mess. It's better to standardize the problem to say -x1 minus 2x2 plus x3 is greater than -5. So I will standardize, and I see I'm happy. This is a standard problem. I have a standard procedure to go to the dual and so on. So you may consider enormous number of special cases. What happens if the first inequality is greater than 0, second one is less than 0, the third one is greater than 0. What should I do? But it's better to just standardize and go faster. Okay?
Yeah, so our standard will be a minimization with the constraints greater or equal to 0.
Yeah, exactly.
Yeah.
Or
And,
maximization with constraints less than or equal to 0. Yeah, exactly. Any more questions about our linear programming problem? Okay, let's move on. Just one more second. Any questions? Everything is clear?
Everything is clear.
Okay, if everything is clear, that's perfect. I'm happy. Whoa, we have done 6 pages. Okay, let's solve something from not from optimization, but from differential equations. Okay, let's go to some differential equations. What we will solve? Exercise. Let's solve something with complex. Let's solve something hard with complex numbers and difference equation with complex numbers. Okay, we have yn plus 2 minus 10 yn plus 1. So plus 26 yn equals to mm, 34. Yeah, I like it. So let's solve this. Any questions about the problem?
Thank you, no question.
Okay, now let's move to the solution. Because we have no initial conditions, we should solve it for general solution. So if we have initial conditions, then we search for particular solution. If we do not see any initial conditions, no, then we are searching for the general solution. Let's find general solution. How we proceed? Okay, what is the step 1? What we will do first?
Solve characteristic equation.
Yeah, you are completely right. First, we forget about the right-hand side. So we solve a homogeneous equation. First step, we solve homogeneous equation. That is yn plus 2 minus 10 yn plus 1 plus 26 yn equals to 0. And then you are completely right. We search for, as we are like in the middle school, we know about geometric progressions, and we just guess that yn is lambda to the power n. And if I plug in my guess into my homogeneous equation, I will get lambda times n plus 2 minus 10 lambda n plus 1 plus 26 lambdas n equals to 0. I cancel lambda to the power n. Ooh. And I will have what is called characteristic equation. lambda squared minus 10 lambda plus 26 is 0. What is the solution of this equation?
5 plus
5.
minus I.
I completely agree. I have two solutions. One is 5 minus I. The second one is 5 plus I. Yes, you are completely right. And then what I should do next?
Well, we can use the Mohrber formula.
Yeah. And honestly speaking, we can. So my first idea that that's only a requirement on external exam. So that's a honest solution. So we have a honest way to write. That's a honest way. I don't understand sometimes why they prefer writing with trigonometric functions instead of complex numbers. I don't see sometimes the point, because at a honest way, we may write it like this: yn is c1 times 5 minus I power n plus c2 times 5 plus I power n, where c1 and c2 are complex conjugate, and they belong to the set of complex numbers. That's a honest way to write, but I don't know why on external exams they do prefer trigonometric form. For me, it's just more complex, more I need. Okay, so that's a honest way. That's okay. That's not a bad style by itself, but on you all, it's better to avoid this. So go to trigonometric form. So, but that's a correct way. If I leave it with complex numbers, it's a. I don't see why they prefer a. For me, it will be uglier with trigonometric. Yeah, I will disappear. Yeah, I agree that in real form notation, I will disappear. So numbers will be like real. Yeah, but the form will be much uglier, like for me.
Isn't it because it's more convenient to take powers in trigonometric form? Well, I mean, here we have.
Dude, that it's for me to take powers. I just write n plus 1. So it depends on what you but okay, let's move on to the trigonometric form. Yeah, let's move on. Okay, how we need to write how we can write 5 minus I or 5 plus I. What is the absolute value of these numbers? The absolute value will be the same, obviously, but anyway, we need it. So these numbers are symmetric. This is 5 plus I. This is 5 minus I on the complex plane. What is the length of these vectors?
Square root of 26.
Yeah, it's square root of 5 squared plus 1 squared square root of 26. Yeah, you are right. And we also need argument of one of them. They have a opposite argument up to the addition of 2 pi. They have positive. They have opposite arguments up to the addition of 2 pi. So what is it? Let me calculate the argument of the 5 plus I. What is the argument of 5 plus I?
Arctan 1/5.
Yeah. And I don't believe that it's much better than the just my answer with complex numbers. So I prefer complex numbers. I think they are more beautiful. But on London exam, they prefer an answer without complex numbers. So be careful. That's my preference. That's my preference. And to have a good grade on external exam, you need to go to real numbers. Okay, I agree that is 1/5. The this is 10 of phi will be 1/5. So because the angle phi belongs to the first quarter, then phi is inverse of 10 of 1/5. Okay, this is phi, and then I can write my answer using real numbers. So how should I write my answer using real numbers? Yn equals to what?
Well, square root of from 26 multiplied by
Yes, square root of 26 power n multiplied by
cosine n phi.
d1 times cosine n phi
And d2 sine n phi.
sine n phi, and we should add that now these constant d1 and d2, they belongs to just real numbers. That's the advantage of that form with cosine of n are tangents of 1/5. That I don't believe it's simpler. Yes, it has no complex imaginary numbers inside it, but like for me, it's more intricate. Just believe me, cosine of n times arctangents of 1/5. That's ugly, but they like it so. Maybe to check whether you can go from complex numbers to real numbers. Any questions?
Yeah, I have a question about this. So if in London exam, we figure out that the answer is a complicated number, how many
Yeah.
points, how many
So
percent?
you write like that. So if you are on external exam, then choose that one to not lose points.
Okay.
So you can always choose. So that the formula with complex number, I like complex numbers. I think they are beautiful. Okay, let's move on. And we have step 2. Step 2, we need to guess non-homogeneous solution. Guess non-homogeneous solution. So we have, oops, I have forgotten that it was 1 plus 2 minus 10, as far as I remember, plus, I think it was like that, 34. Yeah. Step 2, we just guess non-homogeneous solution. So we have constant in right-hand side. So my guess is Yn is some constant d. I check that it does not belong to the set of homogeneous solutions. So my guess doesn't belong to this set. You cannot, by choosing D1 and D2, you can never make this formula equal to constant, with exception of 0, obviously, but non-trivial combination of D1 and D2 will never give you a constant. And basically, so I continue with my guess. I will not multiply it by n. If my guess belongs to the set of homogeneous solutions, then I will multiply it by n. In this case, I don't need to do it. And I just plug in d minus 10d plus 26d is 34. And then like 17d is 34, d is 2. And basically, final answer, I will write it like in the form accepted by on external exam. So my final answer will be 2 plus square root of 26 times power n times d1 sine of n phi plus d2 sine of n phi. And I should be explicit where phi is arctangents of 1/5 and d1 d2 belongs to R. Any questions?
I actually have a question. Why initially C1 and C2 are complex conjugates?
Honestly speaking, it depends on what we are searching for. So I have written, so I was not very specific. What do I mean by general solution? Yeah, what do I mean by general solution? It has two meanings. One is general solution with every yn in real numbers, and as a possible meaning, general solution with every yn complex number. So I was not very specific, but normally if we work with some economics model, like, I don't know, it's popular, like dynamic stochastic general equilibrium models, so which are popular among the central bankers. They have stochastics component inside, but if we abstract for a moment about stochastic component in dynamic stochastic general equilibrium models, so they are used to model real indicators like GDP or maybe logarithm of GDP and so on. So they have so different equations are used in many disciplines, like in physics. You may model something that is complex by its nature, but in economics, indicators we model are real numbers. So it may be inflation, and so implicitly I have made an assumption. So I was not too explicit, but implicitly I made an assumption that every yn I'm searching is real. And in that case, I should add this condition to make the answer always real. If I'm searching for something that is, so if I'm searching for the solution of this equation, but where each y1, y2, y3 is allowed to be complex number, then we have no such requirement in the answer. And that obviously works only for real requirement for each y.
Yeah, but if there was not any requirement, then will the solution be different, or it will stay the same?
First of all, if you are speaking about external exam, then on external exam, even if it's not specified, they mean real solution. So they mean this requirement, and they mean that form of representing the answer. But if you just speak about some general problem outside external exam, when you are analyzing something that is complex by its nature, well, in that case, if you are interested in this case, then the solution process is exactly the same. You just omit, you just forget this condition of conjugate C1 and C2. Just C1 is any complex number, C2 is any complex number, and you have solved the original equation without real requirements. Okay.
Yeah, and in this case, like trigonometric way of solution will not hold, yeah, or we also can.
But D1 and D2 will be also complex numbers.
Oh, okay. Yeah.
So you will change here, so that will disappear. So you will have 4 parameters. You will have A1, A2 in C1, B2, B1, B2, so A1, B1 in C1, A2, B2 in C2, or in D1, D2. So that will change to complex numbers, but not on the exam. On the exam, you will have, so it's better to stick with that choice on the exam.
Yeah, thank you very much.
Okay, thank you for coming. Have a nice day. Once again, I like funny math problems. If you have anything that is not clear during the lectures, so just I will be happy to help you with some funny problems.
Okay.
Okay, see you next time. Bye bye.
See you, Boris. See you next time. Bye bye.
Bye.
Thank you. Goodbye.